Let's get going again. Right, so far we've seen how to do propositional rule induction, and we've seen one way of doing first order rule induction, which is very powerful, and yet we got there by easy steps, because first we figured out how to learn decision trees, then from that we figured out how to learn propositional rules, and then we figured out how to lift that, as it's called, to first order. Okay? But now what we're going to see is a completely different way of learning first order rules. And this is actually a very interesting way, and in some ways a very natural way to do things. And it's the following. You know, for example, how in calculus we define integration as the inverse of differentiation, and then we figure out how to do integration? Right? And this actually happens in mathematics. We define an operation as being the inverse of another operation because we want to be able to invert it, like even square root, right? Why did people invent complex numbers? So they could always take the square root of a number. And this turns out to be very powerful, right? Well, how about we take inspiration from that and do something similar here? So we're interested in the problem of induction, right? This is what machine learning is all about, going from the specific to the general. What is induction the inverse of?
Deduction.
Deduction, precisely. Induction is the inverse of deduction, right? So how about this? How about we formulate induction as the inverse of deduction? In the same way that you can formulate integration as the inverse of differentiation. I would say this is a brilliant idea. It occurred to, I think it was Steve Muggleton, a well-known researcher, back, in the 90s or something. Okay. So right now this is just this very vague idea, right? Let's formulate induction as inverted deduction and take it that way. Let's make it, just slightly more concrete, right? So the classical example of deduction, right, is Socrates is a man, right? All men are mortal. Therefore, Socrates is mortal. Yay, right? Sorry for boring you again with this, but this is our starting point, right? So this is deduction, right? I went from the general, right? All men are mortal. And, one particular thing that I knew about Socrates, which is that he's a man. And from that, I deduced that he's mortal too, right? And, deduction is nice. Like most of computer science is really doing deduction in, various ways. And deduction is something that you can really trust, as opposed to this weird thing called induction that I'm trying to sell you, and you're not sure yet if you're buying. Okay? So what would be the induction version of this problem? The induction version of this problem would be something like this. Socrates is a man, and Socrates is mortal. Plato is a man, and Plato is mortal. Aristotle is a man, and Aristotle is mortal. At which point you say, aha, maybe what?
Men are mortal.
Maybe all men are mortal, right? Once you see enough of those specific cases, your brain is just really good at this. Your brain immediately goes, aha, there's a general rule here. All men are mortal. And then once you've acquired that rule, right, and along comes, some completely different philosopher, let's say, take your favorite philosopher, Leibniz. You go like, or in fact, your favorite person, right, but let's just stay with philosophers for the sake of fun, right? Aha, Leibniz is a man, therefore Leibniz is mortal, right? So from the specific examples you generalized by induction, and from that general rule, then you did the deduction. Notice how they're inverses, right? Because induction went from specific things about specific people to a general rule, and deduction does the opposite. It goes from the general rule back to those specific people or some other specific people. Okay? So this is the way we're going to try to do induction here. Brilliant idea if you ask me, right? But now let's see if we can make this work, right? And fair warning, this is going to be probably the most abstract part of the whole class. But hey, bear with me, and I think it'll be highly worthwhile. So let us try to make this solve a little bit more formal, right? Here's a formula defining what we want to do. And we're going to sort of be playing with this formula a lot, so let's take it one step at a time. Induction is finding a hypothesis, right, from a hypothesis space. And let's call that hypothesis H, right? What do we want that hypothesis to do? right? Again, think back to the analog of integration. Like, what do we want the integral to do? What we want the integral to do is that if I differentiate a function and then I integrate, I get the same function back again, right? This is what that's doing. What is induction trying to do? You can think of induction as providing the missing link. I know that Leibniz is a man, and I want to conclude that he's mortal. What is missing to go from one to the other? This is what I'm trying to induce. Okay? So this gobbledygook here is really just a more formal statement of the same thing. So let's say that xi is my ith training instance, so my ith philosopher, or my ith person in the family. F of xi is what I'm trying to predict, like whether they're mortal or whether they're somebody's ancestor or whatnot. And B is a new thing. B is all the knowledge that I already have. Right? I already have a knowledge base with other formulas, let's say in first order logic, of things that I know about people and about mortality and about children and whatnot, right? Remember, we said early on, and we saw this very clearly, that knowledge is essential to induction. The more knowledge you have, the better induction you can do. If you have no knowledge, if all you have is the data, then you're host. Here, for the first time, we're going to make that knowledge explicit. We are going to call it B. It's my background knowledge. Let's say, for example, I already know that, mothers are parents and fathers are parents. Right? This could be a piece of background knowledge that I have. And now these xi's and these fi's, they are basically my examples. I give you xi, and I want you to tell me whether f of xi is true or not. Okay? So now here's what I want my hypothesis H to do. I want that for every example and its class in my data, D represents my data set, right? In general of a database, right? The background knowledge together with my hypothesis and the example, they allow me to derive, this little t means derives, they allow me to logically derive, they allow me to logically prove that f of xi. You see what I'm saying here? The reason I need the hypothesis is that the background knowledge and the information about the example are not enough to get to my conclusion. Yes, I know that Leibniz is a man and I know all sorts of other things, but I'm not able to show that he's mortal. And my training set says, this guy's mortal. I want a rule that says that. This is what my H is going to be. If, by a fortunate accident, just using my background knowledge and my information in the database, I could already, correctly predict that this person was mortal, well, then I don't need a hypothesis. The hypothesis can be the empty set. Okay? So this is the general agenda of what we're going to do here. Right? Notice that what I have here is just, this is a kind of deduction. It says, if I know this and this and this, then I can infer that. Right? In deduction, I go from B and H and Xi to F of Xi. The sense in which we're going to be inverting deduction here is that what I'm going to do is go from F of Xi and B to H. This really is, in a mathematical sense, a kind of, inverse operation. Okay? And it encapsulates very neatly this whole idea that we've been having that, well, in machine learning, the program, instead of being an input, is now the output, right? That's what our H is here, the program that we're trying to induce. Okay? Any questions? Okay, very good. So we've defined formally what we want to do. Here's a concrete example, right? Nothing like a concrete example to keep things clear. Let's suppose that what we want to do is induce the concept of child. Somebody is the child of somebody. Like, for example, the child of Bob is Sharon, or a child of Bob is Sharon. Okay. And what we have, what is our concept, right? It's over pairs of people. It's pairs of people U and V, such that the child of U is V. Okay. And one such example could be child of Bob is Sharon. Okay. So this is my f of xi. I want to learn to predict that somebody is the child of somebody else. Obviously, this is a very simple example, but it's enough to illustrate the general idea, right? What is my xi? Well, my example is a pair of people here, right? Bob and Sharon. So my xi is everything that I know about them, or that might be relevant to predicting this. So let's say I know that Bob is male. I know that Sharon is female. I know that the father of Sharon is Bob, right? And let's say that in addition we have some background knowledge like parent of U is V if father of U is V, right? This is true. If somebody else's father, they are also their parent. Okay? So first of all, you yourself, just looking at this, can you, if you, so let's do this in our heads first, right? So I have xi and b, right? Are you able to infer child Bob Sharon from these things? Or no? Actually, first of all, just you as a person, right? Do you know, just by looking at these things, so actually, if I gave you this information, right, even without the background knowledge, right, just use the background knowledge that you have about family relationships, right? So I tell you that, Bob is male, Sharon is female, and, the father of Sharon is Bob. Is it the case that a child of Bob is Sharon?
Of course.
Oh yeah, right, of course, right? Common sense, we know that, right? But the question is whether the program knows that, right? Does the computer know that, right? And now you can think of what did you use to arrive at that conclusion, right? You use the fact that if X is Y's father, then what? Then Y is X's child, right? Yeah, you knew that. But the computer doesn't know that. We know what the computer knows, right? The computer actually knows something meaningful and potentially useful, which is that, parent UV if father UV. But that's not enough. From male Bob, female Sharon, father Sharon Bob, parent UV, blah, 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 you cannot infer, you cannot deduce that, child Bob Sharon. And that's the problem. Oops. This is the problem. And that is the problem, is that I'm missing some information to make that deduction possible. So our goal in induction is going to be to figure out what we need to add to the knowledge base to make the deduction go through. And then the deduction goes through. Okay? Any questions so far? So, what did you know that the computer didn't know, right? What could you add to this knowledge base that would actually infer that, a child of Bob is Sharon? Right? We've already seen one of these cases, right? It's the case that, if father VU, then child UV, right? There's also another one, right? What's another one? Well, it's sitting right here. It's the same thing, but with parent, right? Notice that both of these things are true, right? And do both of them allow you to infer that child Bob Sharon? Yes or no?
Yeah.
Yeah, right? In fact, if I know that, father implies child, right? Since I have father here, I can get the child here. This is what we did, right? This is the easiest route. Okay? But, and this again is going to be a general theme, is that is not the only way. There's going to be more than one way. If I know that parent implies child, right? Then because I also know that father implies parent, I can say, oh, father, therefore parent, therefore child. Okay? So there's more than one way. Which means that my deduction has more than one inverse induction. Which shouldn't surprise anybody because, for example, the same thing is true of integration, right? Remember, when you integrate something, it's only up to a constant. That constant could be anything, so there's more than one answer. Similarly, right, there can be more than one square root of 1. Right? There's plus I and there's minus I. So again here, there's more than one thing that you could add to your knowledge base that could actually make the induction go through. And we're either going to need a way to choose between them, like say we pick the simplest, the one that makes the knowledge base smallest, or we add all of them, let's say. Typically we use the former, obviously. Right? Notice also the following important thing. Did I use in this deduction the fact that Bob is male? Not really, right? I never used that. Did I use the fact that Sharon is female? No, not either. And as always, what this means is that my database is going to have a lot of information that is irrelevant to the problem at hand. And a big part of the job of the machine learning system is to get rid of that. Figure out what's relevant and figure out what's not relevant. It would be a good day on which all the information that we have is relevant to the problem at hand. Okay? Questions? All right, so this is what we're going to try to do. Now let's, so here's the statement of the problem, right? So what we have now, right, just from computer science and logic and whatnot, is deductive operators. And we can express this as in the following form, right? If I have A and B, I have a function f that produces C, right? Think of A as the fact Socrates is mortal, and B as the fact, as the fact Socrates is human, and B as the fact all humans are mortal, and C as the fact, Socrates is mortal, right? So F is deduction. F is the operation that transforms A and B into C, right? And in logic, we write that as AB derives C, okay? But these two things are really just different ways of saying the same thing, okay? And our goal here in the rest of this class is going to be to figure out inductive operators that actually do the opposite. So what's the inductive operator? By analogy with this here, O of BD, right, is something that you give me the B and the D, right, and I get out the H, such that the B and D and the H then now allow me to derive, the F of xi, okay? So again, we're looking for a function, except that now it's an inductive step that's being done as opposed to a deductive step, okay? All right, so before we go into this, let us see what the pros and cons of doing this are, because there are some very important pros and some very important cons, and you need to be aware of both of them. One of the first obvious pro of this is that the previous case that we've been talking about up until now, including decision tree induction and propositional induction and FOIL and whatnot, is really what you get in this case when your initial background knowledge is nothing, or at least is a very weak background knowledge that is not made explicit in declarative form, right? So if I take what we're doing here with a case of no data, or of no knowledge, right, then this just becomes the case that we had before. So this is nice because it generalizes what we've already been trying to do, right? But now, of course, it brings in something very important and new, which is now I can make my knowledge explicit. It's my background knowledge B. That's what I already know, right? I actually have a list of formulas stating that I know that, mother implies child and so on and so forth, okay? So I can make that knowledge explicit, and therefore I can do things with it that I couldn't when it was implicit, as in the case of learning a decision tree. And of course I have a lot more flexibility. I can put in knowledge that I know, which I couldn't do with the decision tree, and use that to help my induction, and have the induction complete the knowledge and build on it. And moreover, this actually suggests a new type of learning algorithm, right? What I'm going to do is I'm going to look for H, not blindly, not just by some, greedy search that's trying to, hit the right things in the dark. I have all that background knowledge to guide my process, right? When you learn, you do not learn from scratch. God forbid that you always be learning from scratch, right? Imagine being in this class, while being a 6-month-old baby, right? That wouldn't work, right? You'd cry a lot, and that wouldn't be fun, right? You're always learning by building on top of the knowledge that you already have. The methods that we saw before, they basically are the analog of the newborn baby, like they have something in their brain, very important, right? But they really don't know anything much yet. Now we can actually be guided by our knowledge. Okay? So those are the advantages. There are also some important disadvantages, which is important to be aware of. The first and very important one is that this doesn't allow us to deal with noise. Noise is very important in the real world. Some of my examples are misclassified. Somebody mistyped something. My sensor reading was noisy, right? This email was classified as spam, but it shouldn't have been. You just pressed the wrong key or something. Okay? Deduction does not like noise, right? Deduction is all about complete precision, and it's either true or false, and you say exactly what you mean. So these methods, at least as they stand, cannot deal with noise. There are, of course, generalizations and variations that can deal with noise. We're not going to touch on them here, but they add complexity. So this is one minus. The other minus, which has probably already occurred to you, is the following, right? Remember when we said that large hypothesis spaces are good, right? Because they mean you can learn lots of different things, right? So you want the truth to be in your hypothesis space. On the other hand, large hypothesis spaces are bad, because they're expensive to search, and they really increase your chances of overfitting, right? And the hypothesis space that we're looking at now is huge. First of all, not only is it first order, right, instead of propositional, that's already a huge jump, but now it's going to involve playing around with all this knowledge, right? So I have a much bigger combinatorial explosion than I had before. So the bottom line is that these methods are much less scalable than plain propositional decision tree and rule induction. And that's probably the biggest reason why they're not as widely used. Okay? They at this point in the current state of the art, these things do not scale to say Facebook, right? I don't think Facebook is using this because they want to mine a network of, 1 billion friends, and this stuff doesn't scale to 1 billion friends. But it might scale to millions. So for some problems, you can use this. And moreover, in this trade-off between knowledge and data, if what you have is a lot of data but not a lot of knowledge, then this is probably not the right choice for you, right? Use one of those fast propositional methods. On the other hand, if what you have is a lot of knowledge but not a lot of data, those methods can make use of the knowledge and the data is not enough, but this stuff might be exactly what you need. And to take an example of an area where this has been applied with great success, drug design, right? My molecules, you can think of them as graphs. I want to know which molecules, for example, cause cancer, or which molecules actually stop cancer, right? I can represent them in this form. I often don't have a lot of data because at data point, this molecule is carcinogenic, or this molecule binds to this virus. That knowledge is very hard to come by. It requires a lab and experiments in the lab. On the other hand, there's like reams of biology papers and textbooks out there with biology knowledge. And I can write down that knowledge. This is what makes a molecule carcinogenic, or this is what I know about organic chemistry, right? The knowledge doesn't have to be directly about the task. So in those cases where I don't have a lot of data but I have a lot of knowledge, this might be what you want to use. Okay? All right.